This is Chapter 4, Sensation and Perception, Part 3. Alright, so we have discussed sensations in the previous two video lectures, and now we're going to move toward perception. The major senses of perception, the process of selecting, organizing, and interpreting incoming sensation into more useful mental representations of the world. So normally our perceptions would agree with our sensations. However, when they don't, the result's an illusion or a false or misleading type of impression that's produced by errors in the perceptual process or by actual physical distortions, such as in a desert mirage. So what we're going to be discovering is how, when we are applying psychology for more information about how illusions provide psychologists with a tool for studying the normal process of perception. Be careful, though, not to confuse illusions with hallucinations or delusions. There is a difference. Okay, so in almost every situation, we are confronted with more sensory information that we can reasonably pay attention to. There are three major factors that would help us focus on some stimuli and ignore others, those being selective attention, feature detectors, and habituation. Now, there are certain basic mechanisms for perceptual selection that's built into our brain. For example, through the process of selective attention, the brain can pick out the information that's more important to us and will discard the rest of it. Whereas in humans and other animals, the brain also contains these specialized cells, and these are called feature detectors, that being it responds only to certain stimuli. So A is selective attention, and here when you are in a group of people, for example, you're surrounded by various conversations, you can still select as well as attend to the voices of the people you find interested. If we gave another example of that, think about attention in terms of what's known as the cocktail party phenomenon. Have you ever noticed that how you can suddenly pick up on another's conversation if someone in that group mentions your name? Well, that's that selective attention at work. So with feature detectors, studies with humans have been able to find that feature detectors are found within our temporal and occipital lobes, and that responds maximally to our faces. Problems in these areas can produce a condition called prosopagnosia, and that means prospano is face, as well as agnosia means you don't know, failure to know. Interesting enough, people with prosopagnosia can recognize that they are looking at a face, but they just can't seem to know whose face is reflected in the mirror, even if it's their own, or a friend, or a relative for that matter. Okay, the next one, habituation. Now, these two girls, right? Their brains, they choose to ignore their painful braces. Now, some sensory adaptation might have occurred, but over time, the girls' pressure sensors would have fewer messages to the brain. So, understand through habituation, basically the brain is saying, okay, we do this so much, enough of it, that it doesn't have to really pay attention to it. Therefore, that detail wanes and weakens because it's something that's constantly going on. All right, so we love doing the Mythbusters, and the only thing I want you to do is you're going to take time and pause the video, take time to read this. And I don't know if any of you seen that movie Black Swan. You might remember that was a scene that showed Natalie Portman, who played Nina, bending her legs like a swan, having webbed feet and growing black feathers. Here's the question: were these illusions, delusions, or hallucinations? So, for psychologists, the differences are extremely important because hallucinations are false sensory experiences that occur without an external stimulus, such as someone may be hearing voices during a psychotic episode, or If it's a visual type of hallucination, they might see flowers pulsating, particularly after using drugs such as LSD, as well as other type of hallucinogenic drugs. Now, delusions, on the other hand, these refer to false beliefs, most times persecutory or of grandeur, and many would accompany those drug or psychotic experiences. So illusions is just more or less perception of the trick of the eye, um, not in so much as hallucinations in which it's coming due to a psychotic break, something that's not there, being there for a person. Um, Hallucinations can come as visual, auditory, tactile with touch, whereas illusions is just simply seeing things differently based upon how it was set up. Another page you want to try and pause, you can look at which of the two horizontal lines will be longer and see if you can figure that out. Okay. And one more. Again, pause it, take a look, and see if you can tell which one will be longer. Is it the horizontal or is it the vertical? Or are they the same length? What's the illusion? And still more illusions. But yeah, test these out for yourself. Actually get a ruler, pause, get a ruler, and see about whether or not uh, this shows the longer or shorter length. And then let me know. You can just jot it down in the assignment. Okay? All right, so moving on. Now we're going to start looking at the organization or the form of how we form perceptions. Raw sensory data are like the parts of a watch. They must be assembled in a meaningful way before we can actually say they're useful. So when we organize sensory data in terms of form, constancy, depth, and color, we utilize just Gestalt principles. Now, Gestalt principles are based on the notion that we all share a natural tendency to force patterns onto whatever we see. Although these examples of Gestalt principles that appear in this figure are all visual, each of the principles applies to other modes of our perceptions as well. So, for example, the Gestalt principle of contiguity cannot be shown because it involves nearness in time, not visual nearness. So you may also have this experience with oral figures, the ground effects, or at a movie theater or concert when there was a conversation going on close by, and you couldn't sort out what sounds were going on in the background, or you wanted to be your focus. Form perception, Gestalt psychologists, they are among the first to study how the brain actually organizes sensory impressions into a Gestalt. Gestalt is a German word that's meaning form or whole. Now, these emphasize the importance of organization as well as patterning in ability for us to perceive the world in a stimulus rather than just perceiving its discrete parts as separate entities. Gestaltists proposed several different laws of organization that specifies how people might perceive forms. The most fundamental Gestalt principle would be the organization is our tendency to distinguish between the figure, which which would be the main focus of attention, as well as the ground, which is that background or our surroundings. Now, in terms of depth perception, here we're looking at three-dimensional world. It's the ability to perceive the depth as well as distance of objects, as well as being able to look at height as well as width. These are important as well. We'll usually rely most heavily on vision to perceive distance and depth. So depth perception is learned primarily through experience. However, research has been able to demonstrate that using an apparatus like the visual cliff would help to show some depth perception is actually innate or inborn. One mechanism by which we'll perceive depth is our ability or interaction of both eyes to produce binocular cues. It's those others that involves monocular cues, which would work with each eye separately. So looking at this figure on the slide, you see a crawling infant. Now the crawling infant's going to hesitate, or they might even refuse to move at all when we're talking in terms of the deep end of a visual cliff. If they think they're going to fall off, they'll stop. This indicates that they kind of perceive the difference in depth, although they're an infant and they haven't learned it yet. The same can hold true for baby animals that may walk almost immediately right after birth. Even 2-month-old infants show a change in heart rate when they're placed on this deep versus shallow side of a visual cliff. Now, here we're having fun again with taking time to pause the video, and I want you to make sure you take time to read the instructions, but this is looking into our depth perception and the binocular depth cues. Our retinal disparity can be demonstrated by the hole in the hand illusion. And pretty much what I want you to stop and do is kind of take some roll of sheets of paper and put them into tubes. Okay, roll it up and make it into a nice little tube. And while you're holding the tube in your left hand, look through it with your left eye. Then what I want you to do is take your right hand and hold the tube, and hold it next to the far end, okay? So with each, when you're looking far away enough through both eyes, you're going to kind of see a hole that's going right through your right hand. Now, is there a hole in your hand? Of course not. However, the brain's not able to reconcile that different view coming from the two eyes. So it'll choose to see through the hand and out of the tube. When we're applying this retinal disparity in convergence, it's kind of where you see why coaches are always reminding players to keep their eyes on the ball, because sometimes the brain is going to want to go right through. Convergence and depth perception are better when you're looking directly at an object rather than out of the corner of your eye. Thus, if you turn your body or your head so that you look straight at your tennis opponent or the pitcher, you will more than likely accurately judge the distance of the ball, and thereby you'll be more likely to swing at the right time. So pause it, read it, try it out for yourself, and then you'll see if it actually works for you. Now, the binocular, which of course is two eyes, cues for retinal disparity and convergence that's inadequate in judging distance longer than the length of a football field. However, luckily enough, we kind of have several monocular cues, which again, monocular means one eye. We kind of have those cues available separately to each eye. So artists, use monocular depth cues such as linear perspective, light and shadow, as well as the interposition to give depth to a flat image. Like when you take, you've seen those artists, Julian Beaver is one of those artists that do some fantastic work of arts on the sidewalks. And when you look at it in a particular way, it's actually looking 3D, three-dimensional. It looks like it's coming at you, or it looks like it's a real person or a real chair there. That illusion. That's what I'm talking about in this sense. Now, we also need to talk about motion parallax, which is the relative motion, basically. This is referring to the fact that when we are moving, close objects appear to move fast, whiz by us, whereas objects that's kind of far and distant from us seem to have a more slow and stationary type of movement. It's kind of real. It's like it's almost not moving at all. This effect is easily seen when traveling by a car or by a train. In terms of talking about accommodation, that's when the muscles adjust the shape of our lens as it focuses on an object, and then action potentials are going to occur. It's going to be sent to the brain, which, excuse me, interprets the signal to perceive distance, and that's looking at near objects. The lens will then bulge. So far objects, the lens will then flatten. Okay. Moving into perceptual constancies. Now this is the tendency for the environment to be perceived as remaining the same, even when there's changes in our sensory input. So things would seem to grow as we got closer to them, or to be able to change shape as our view angle changes, as well as to change colors at light levels that's been changed. There's four, and the four best known constancies that we have within our perception would be size, shape, color, and brightness. So please make sure you stop and take a look. Make sure you have a good understanding about those four, and we'll move on. Now, continuing on perceptual constancy, we kind of have to take a look at that shape constancy. So we know what a quarter looks like. The slide is showing you a quarter, right? As you change the direction, as you're turning it, if you're rotating it around 360, you're going to see that it starts out flat if you start it this way. When you turn it this way, then you have more of a vertical flatness. Then you turn again, you're going to see and show how the shape changes yet again, and then there's back to it being round and flat. Although we're seeing all these changes, if it wasn't for the constancy, then we would think that we're holding a different object each and every time. But because of perceptual constancies, we know that that shape is relatively going to be the same, even though it's tilted and turning, and we know that this is a quarter. Now, when we're talking about, I don't know if you've ever seen the Ames room. The Ames room illusion, it pretty much makes where two people could be standing there, and if it's a child, for example, on one side, the child looks like they're a giant compared to the adult that's on the other. Well, our eyes, although there's a constancy in size and shape, because of the way the room is set up, it is actually making it where the child is lifted. The floor is actually tilting, so it makes the child look extremely larger than the adult, even though we know that's not to be the case. We got to remember that perceptual constancy is that tendency for the environment to be perceived as remaining the same, even when there's changes in our sensory input. Okay, so in this illustration, although we know that that child is smaller than the adult, the illusion is that it allows us to see them differently. But our brain kind of knows, even though it's seeing a difference and there's illusion, we kind of realize that it is an illusion because of it. Color constancy and brightness constancy is where we might look at a dog and you see the two dogs and one look darker than the other, and that's because of the hues of the lights and how the lights might be changing, but in reality the two dogs are the same color. Alright, now here's another beautiful fun area in which I want you to just do this on your own. You can pause the video at any time. In terms of looking at color vision, I want you to, as you can see on the flag, that there is a dot in the middle of that flag. Look at it for 60 seconds. Then I want you to stop and look at a white surface, okay? Be that if it's a table or have a piece of white paper by you. After you looked at the flag, the dot specifically, take a look for 60 seconds, then move yourself to that white surface. What's going to happen is you're going to actually see a regular red, white, and blue flag uh, on that white surface. Right now in the slide you see it as yellow, black, and green, but if you stare long enough and then look at that white, it should turn red, white, and blue. Okay, can anybody think about how this relates to the opponent process theory? Well, our color vision is remarkable as our ability to be able to perceive depth and distance. We as humans, we're able to discriminate among several million different hues, and we've been able to conduct research in several cultures that would show how we all seem to essentially have the same type of color world. But the thing is, with the studies of infants when they're old enough to focus and move their eyes, it's been able to show that they're able to see color nearly as well as an adult can. Although we know color is reduced by different wavelengths of light, the actual way in which we perceive color is kind of like a matter of a scientific debate. There's some controversy. In the past, we've been able to say that there are two theories of color vision, that being the trichromatic, which is a three-color theory, and then there's the opponent process theory. With the trichromatic theory, word tri means three, and chroma meaning color. Yeah, this was proposed by Thomas Young way back in the early 19th century. And it was later refined by Helmholtz and others. And according to this theory, pretty much they're saying that we have three color systems. And they've called them out, and that one system is maximally going to be sensitive to the reds, another one's going to be more sensitive to the greens, and then the third one being sensitive to blue. Now, the proponents of this theory kind of demonstrates that mixing the lights of these three colors would help to yield the full spectrum of colors that we actually do perceive. Unfortunately, though, there's flaws within this theory. One would be that it doesn't explain color after effects. You know, like we just talked about in terms of the flag. You've seen it yellow, black, and green, and then it turns red, white, and blue. It's not really given a good explanation for that. But the opponent process theory that's proposed by Ewald Heron later in the 19th century, they also suggested that there was a three-color system. But here, Heron said something a little different. He suggested that each system is sensitive to two opposing colors, that being blue and yellow, or red and green, or black and white, and basically in an on and off type fashion. So in other words, each color receptor will respond either to the blue or the yellow, or the red or the green, with all the black or the white systems responding different in those brightness levels. This theory kind of makes a lot of sense though, because when different color lights are combined, then people are unable to be able to see the reddish greens or bluish yellows. Matter of fact, when red and green lights or blue and yellow lights are kind of mixed in equal amounts, we'll actually see white. So back in 1964, George Wald as well as Paul Brown, they kind of showed that we do not have to have three kind of cones in our retina, and kind of confirmed that there's a central proposition of that trichromatic theory. At the same time, Dave Velos studied electrophysiological recording of cells within our optic nerves and our optic pathways to the brain. He was able to discover that these cells would respond to color in an opponent fashion within our thalamus. Fashion in the thalamus. And that findings was able to help to reconcile that once competing type of theories of the trichromatic and the opponent process theories. Now, today, we kind of know that color is a process of the trichromatic fashion at the level of the cones within the retina, as well as in an opponent fashion at the levels of the optic nerve and the thalamus. They kind of work all hand in hand. So if you were wondering which theory that we discussed as far as the trichromatic and the opponent, they're both correct. Okay, they're both utilized. They both show and work in the same type of fashions, and this is something that you need to make sure you remember for a test question. All right, here I want you to pause this again after I finish speaking, just for yourselves to be able to test yourselves using this slide. Color deficient vision, most people perceive that there's three different colors, that being red, green, and blue, and these are called the trichromats. However, there's a small percentage of people that would have a genetic deficiency in that red-green system, or even the blue-yellow system, or both of them. Those who perceive only two colors are called dichromats, and people who are sensitive to only the black and white system would be called monochromats. And here, this is where there's total color blindness. So if you'd like to test yourself for red-green color blindness, I want you to take a look at this figure and from your textbook read on and follow follow the instructions, okay? And tell me what you see. Hopefully you'll be able to see the numbers that's within, and if not, then you might have some color blindness going on. Now, what I'd like for you to do is imagine that your visual field is suddenly inverted and is reversed. Things you expect to be on your right are now going to be found on your left. And then there's things that you might expect to be above your head, you're now seeing them below your head. Do you think you could ever adapt to living upside down? So in order for, of course, this was a research question. And in order for that question to be answered, George Stratton, who was a psychologist back in 1896, well, he kind of invented this special lens, and then he went around wearing them for about 8 days. So the first few days he wore them, he kind of had a lot of difficulty navigating within the environment and being able to cope and deal with everyday tasks. By the third, mm, by the third day, he kind of seen that he was able to was walking through these narrow spaces and between pieces of furniture that require much less care than he thought. Was able to watch his hands as they wrote without hesitating or becoming embarrassed. So by the fifth day, Stratton had almost completely adapted and adjusted to his strange perceptual environment. And when he later removed the headgear, he automatically readjusted back to everything being normal, to what he considered normal. So his experiment pretty much illustrated the critical role how perceptual adaptation plays in our lives and how we are able to interpret information from our brains. That information the brain takes in and gather and tells us what it's supposed to be or what we think it should be. Without his ability to adapt his perceptions to a skewed environment, he probably wouldn't been able to function. Our brain's ability to restrain itself to new surroundings allows Stratton to create coherence out of what he otherwise saw as chaos. So we want to make sure that we understand the three major factors, that being about perceptual adaptation, our perceptual set, as well as a frame of reference. And when we talk about perceptual adaptation, this is our brain's ability to take time to rewire itself and adapt to any type of chaos or skewed environments. Now, how we perceive people Objects or situations is also affected by the frame of reference or context. Think about an elephant. An elephant is perceived as much larger when it's next to a mouse than when it stands next to a giraffe. Okay? So our perceptions of people, objects, or situations are going to be affected by that frame of reference. And an elephant, again, think of the elephant compared to a little tiny mouse, and then you got the big elephant. But then when you put them next to a giraffe, giraffe is real tall, so you don't see him as big anymore. All right. We're going to stop here, and on the next and final slide, we'll be talking about sensation versus perception. So, yeah, it's a very long chapter, but we are working through it, and we're almost at the finish line. So I'll see you in the next part.